we go through. We have a lot of material today, so we're trying to make. I try to be as concise as possible, and then we're going to introduce the 3 early adopters that we have. Going to come up here and talk about their experience with Pheonix as well. So I will go through first, and just to give you a brief introduction of what Microsoft is trying to do with Pheonix, and also what my team is trying to do as well. So we can see a little bit of both. Let's see where we're going with it, and what we're trying to use with it, and how do we expose that to the academic world as well. So let's move forward to, introduction. I'm sorry. I'm Hoi Vo. I'm leading the binary technology team. Basically, it's a team that eats up binary and spit it out and then trying to do funny things with it. In a word, basically, on the performance side, or basically static analysis, and the dynamic profiling-wise, that's what our team is doing. So today I will be trying to introduce our three early adopters. Mike Smith from Harvard, Rajiv Gupta from University of Arizona, and Brad Carter from UCSD. We're going to go through experience with them to see exactly how they use Pheonix in their research, and how do we work with them as relationship-wise to go forward in their work as well. So basically, we're going to go through the current status of Pheonix, and then we introduce the 3 early adopters. So that's the agenda. So I will go briefly. If you see John LaForce's talk already, I will not go deeply into the Pheonix architecture itself. But before we go on, to put things into context, I will try to go through and show you a little bit what Pheonix is about and what our part is going to contribution to the whole picture, and then you can see exactly how the research academic portion is going to fit in. So let's look at Pheonix right now. It's just a black box. It's basically consisting of several readers. And right now the C++ IR reader and the CR reader, which is basically MSIL reader. And from these 2 OBJ files, we build an IR. We call it high-level IR. We have phase operating on the IR itself. And then medium IR, which is basically the lower level, which is have all the global optimization phases running as well. And then the lower, less level IR, and it has different phases activated on that, which is like register allocator, lowering all the goodies part about code generation. So the part about our team added to the whole picture is the Win32PE reader. So if you are familiar with Vulkan, what John mentioned in the past, we use Vulkan to edit binary so we can do profiling for optimization purpose, code transformation, binary translation, that kind of work that we do. So for Pheonix, we try to add the same functionality so that way we can read in PE that will compile either through Pheonix or through the current compiler as well. And the reason we want to do that is because to facilitate the part about the research portion of it. So if you have a binary that has been compiled already, we want to go through with it and try to figure out how we can break it up and raise it to MIR. That's the part we're trying to build right now. It's a tough one because going from code that doesn't have a lot of symbolic information, raise it up to the level you can start doing things with it is pretty tough. But reading back into LIR and write it back out, we already have it done so far. So part of the Pheonix, basically, we have a conf writer, which made it OBJ back file again, and then the PE writer, which is Win32PE. And circulate all of that is a managed API layer that allows you to write tools. So analysis tool, instrumentation tool, and optimization tool, you can see how the early adopters will be using it in their work as well. And part of the whole thing is we have a PE writer on the back end to write out a new PE file or the OBJ file, which a traditional compiler usually do. The IR diffing part is the part that we're using to compare 2 IR together. So if we have a binary build with a previous tool set, and then we compare it to the current tool set. When you have a new tool set, you compile a second day, you change your source code and decompile again. So you compare the 2, and then we can start doing interesting work against them. Part of the work we do that is to allow us to propagate profile data from one build to another, for example. So for example, you can replace a phase inside of the Pheonix framework as well, or you can add a new phase. So that way, basically, you can control a lot of things that was going on inside of the IR itself and actively participate in the whole picture as well, and not just basically stand back and just take the whole thing as one black box. Of course, all these things going through the managed API layer. You notice that I said managed because we don't have an unmanaged API layer right now. And we don't plan to build one either because if we do, it's going to be like 800, 900,000 of APIs you're going to be messing around with. It's not fun to deal with. So anyway, so that's the main picture of Pheonix. Let me jump ahead. I would love to answer questions, but because we have a lot of materials, I would love to talk to you, everybody, at the end of the sessions. So from the perspective of the binary technology team, what kind of things do we do right now? If you pass by the Demo Fest booth 17 tomorrow, we can give you a more in detailed demo of what's going on. But the focus mostly is on CIL, which is MSIL, static analysis, and also we try to do everything that we can at the binary level right now. So you can read an MSIL or Win32P XCD6, and we can modify the IR for profiling purposes. We build a symbolic execution simulator underneath, so we can find out whether there's a path that was basically worthwhile to go down to do the analysis or not, and not bother with it. We build an interposition variable tracker. Right now, this effort is one of the security push. Basically, people are trying to parse source by hand and trying to track variables by hand, which is not a very good way to do it. So we use Pheonix to see if we can help the process. And right now, it reads an MSIL, break it down into the IR. Given a variable entry point, it can search all throughout the whole IR to figure out at what point in the source code it reads data from into that variable and where does it propagate it to. So that's one of the code review tools that we built for one of the security team at Microsoft. Profiling, of course, the traditional basic block and edge flow profiling mechanism that we can do as well. And then we're trying to build a performance analyzer, which mainly is the we cannot really write out optimized binary yet at this point, but at least at this point we can generate hints or try to figure out how to help the user do a better job at what their work is doing, and feed it back to the compiler as well. So without further ado, I would love to introduce Rajiv Gupta, Dr. Rajiv Gupta, who's been working with us from University of Arizona on his work on the precise dynamic profile slicing.
Okay, so actually we are using Pheonix to do some of the profiling work that we started a couple of years ago, and I have two students who are actually using it. One of them is with Hoi, and Hoi is hosting him, and that's been very useful in trying to learn about the system. So let me basically just briefly describe the project we are working on. So the first thing we are looking at is dependence profiling. There's a lot of work done on profiling, profiling values, addresses, control flow. Dependencies is another thing that you can profile, and not much work has been done on profiling dependencies. However, there are a lot of uses for this in compiler research, in architecture research, and so basically we are looking at the problem of dependence profiling. And basically the first step we took in this direction was to actually collect all the dependencies that are exercised during a program execution, all the data dependencies, all the control dependencies, and and the issue really is when you collect all the information, how do you compress it down, how do you maintain it in a way that it can be easily accessed, analyzed by the users, which are essentially people doing research in compilers or architecture, where they want to look for different types of characteristics in this data. And so we started with this first step, and this year we had a paper on this which describes how we compress down the data dependencies. So basically, when I use the word compress, usually you always think of gzip or these type of compression things. The problem with those compression techniques is once you have compressed, you have something which is taking less space, but when you want to use it, it's not very good. I mean, you have to uncompress it. So the basic idea here is that even though we are doing compression, but it's not the traditional type of compression. It's basically, we are trying to, in very simple terms, we try to find the information that we can infer, so we don't have to save, and by doing variety of transformations or on the program, we can further reduce this so that we have to remember less and less information, and we can infer more and more information. And of course the second part is that you can infer it, but then when you infer the information, it should be fast. So if you are interested in the details, actually it's in a paper which appeared in PLDI this year, which describes how we do this. Now my student who's working with Hoi during the summer, what he's doing is he's looking at essentially approximations of the data dependence history. So essentially, just like if you're familiar with path profiles, we can take a program, we can identify a set of paths in the program, and we can instrument the program to collect frequencies of those paths. We're doing something analogous for the data dependence chains. So in other words, if you look at the whole data dependence graph, you can break it down into some sort of chains or smaller chains, and then you want to instrument the program to collect that. And that's essentially what we are using Pheonix for, to do the instrumentation, collect these profiles. If once we are done with that, the next thing we want to do is this piece of work where, as I was saying before, people have looked at value profiles, address profiles, control flow profiles separately, and I just described in the previous slide that how we can do dependence profiles too. Now if you can do all of these, then why not have all of these available to you together? Now again, if I give you one file which contains control flow profiles, another with value profiles, another address profiles, it's not going to be very useful, because the moment you want to use more than one type of information, you need to relate, like when the control flow went like this, that's when this address was referenced. So in other words, you want to relate the different types of profiles to each other. So what we have done is we have designed basically you can think of it as a representation where you have a static program representation, you annotate it with all the profile data that you have, all the values, addresses, dependencies, everything. And the advantage of that is that once you have a program representation, you know how to traverse it, you know how to do, for example, data flow analysis on it. And while you're doing any kind of analysis, you will have access to all the information that you saved, when you need it, where you need it. So for example, if I solve some data flow problem and I want to know how often this thing is true, I mean, as a side effect of doing the analysis, I can easily compute the frequency of whatever event I was analyzing. So we have a representation, we have done some preliminary experiments. So for example, we can in memory we can keep maybe these type of traces for 2-3 billion instructions, all the values, addresses, control flow, everything. And of course what we like to do is, as soon as we have the dependence stuff implemented, we'll go on and implement this complete piece of work in Pheonix. And actually, why Pheonix? Because you may say, I mean, you can do it otherwise. In fact, we are doing it in other platforms also. I think one of the attraction for me when Hoi first contacted me about this was that the potential that you will be able to put in a lot of programs, because this is a robust infrastructure, potentially written in different languages that you may get from various places, plus of course the programs that Microsoft may provide, which basically large pieces of code, large code bases. And so that's one of the things I think this kind of tool I found attractive, that you will be able to analyze real programs, not small programs, because usually if you build the infrastructure and it's not robust enough, then you're just always struggling to get anything real through it. So for me that was one of the biggest motivating factor. This is just a picture of what I just described. But what did we do so far? I mean, we have been using it for a few months, but the first thing we did was, when we got this, we just tried to do something very simple. Collect the address profiles. So we instrumented the load, store instructions to collect the address profiles. And so that we just did so we could actually learn a little bit about it. They were, as John showed in his talk, you could instrument, for example, for collecting basic block counts and so forth. So we collected addresses. That made us read the code and understand the interface and a little bit. So that was a very painless process. Now what we are doing is the thing that I was talking about with the data dependence chains. Now that is a little more involved, because it involves not only instrumentation, but it also involves transformations that need to be applied to the intermediate format. And the reason is that essentially what we are doing is when we are taking these chains that we want to profile, and when we instrument, before that we go through a transformation phase which will turn the frequencies of certain data dependence chains into frequencies of certain paths in the program. So that's the transformation step. And once we know how to profile paths, and then we can basically use the lattices path profiling, or essentially extensions of it to do that. So this is a little more interesting because we get to play with the intermediate representation as well as we do the instrumentation. If we are successful in that, then I think we have the basic pieces, so we can do the work I have described on the previous slide to generate the full traces. So our experience has been quite good so far, because first of all, as John was telling in his talk, I mean, you get some examples. So initially you can get started from there. And actually one of the things which helped us a lot was a close interaction with Hoi, because he was very available and he actually visited us and he answered the questions. He sat with my group and he went through everything. And so that was very helpful, and the documentation is very good. My student who's working here, one of the things he has reported is that when he's working here, because the source code is available, it's helpful because you can understand when things go wrong, why they went wrong, and then he can, with the help of experts here, he can find ways around the bugs. So far we have been basically doing things at the lowest LIR level, the lowest intermediate representation level. But there is a lot of what we like to use is at the next level. There's a lot of aliasing information available, and some of these transformations that I was talking about, they are actually driven by the aliasing information. The better information you have, the more effective those transformations will be. So as soon as we finish what we are doing now, which is the profiling of the dependence chains, we'd like to learn about the alias analysis and then work on the whole traces. So I mean, that's all I have to say, but if you have any questions you can ask me. Yeah, right.
So next will be Mark Smith from Harvard. We will be talking about graphical representation, the same paper that he has announced with API. So Mark will experience with Pheonix as well.
Okay. Thank you, Hoi. So our project was to replace the linear scan register allocator that comes in the back end of Pheonix with this generalized graph culling register allocator that we've been working on, that Hoi just mentioned, that we recently published at PLDI. And what this did was give us the opportunity to get into Pheonix and look at what kind of support Pheonix had for doing machine-specific optimization, and it allowed us to evaluate our new algorithm on multiple platforms. We have a research compiler back at Harvard that we've implemented this on, and now we've implemented it within Pheonix too. So what I'd like to do this morning, this afternoon, whatever it is tell you a little bit about our algorithm so that you have some feel for the scope and the depth into which we went into Pheonix, and then give you feedback on our experiences in using the system. So back in 1981, Chaitin showed how we could do graph coloring to solve the register allocation problem. And key in his approach are two assumptions that I've listed up here. First of which is that all of the registers that you're trying to allocate for are interchangeable. That is, they can be used equally well in any program context. I'll get into a little bit more detail what I mean there in a second. And also that they're all independent. That is, writing to any particular register is independent, doesn't change the value within any of the other registers. Unfortunately, if you look at modern architectures out there today, they violate either one or both of these assumptions. So what happens is people will build off of the Chaitin's approach to build a graph culling register allocator and then insert some hacks in order to actually make it work for the target architecture that they're interested in. And for this audience, I'm just going to focus on x86. It's interesting to most people who are interested in Microsoft's software, and show you that it actually violates both of these assumptions. On the left-hand side, I've listed some register classes. We're just focusing on the integer register set within the x86. As most of you know, there's about 8 registers in there, 6 of which we can use for allocation. And if you look at how the program variables are used by the different instructions inside of an x86 program, you'll see that I can't always use all of the registers for all of those register candidates. In some cases, I can only go about using the accumulator-like registers as opposed to the accumulator and index-like registers. Sometimes it's a 32-bit context, sometimes it's an 8-bit context, and so forth. So this breaks up our register file into different classes, which violates our assumption that there's one set of registers in our architecture and they're all interchangeable. And what we'd like to be able to do is allocate with all of these other register classes in mind so that we can come up with the best allocation. Also, for those of you who are familiar with x86, you know that if I write to EAX, I'll also change the values in the register names AX, AH, and AL, and vice versa. So we have to keep track of this aliasing as we go through and do register allocation. So we build these alias sets and register classes in our approach, and we end up with a solution, which I will give you a brief introduction to today, that allows us to simultaneously allocate all these overlapping classes so that we come out with a good allocation, and it handles the register aliasing directly and very cleanly. A couple of other things that were important to us as we went through this is there's a lot of work that has been done based on Chaitin's original approach. And we want to make sure that our generalization of his approach allows you to continue to use all those different kinds of register allocation approaches too. So we're going to try and maintain efficiency and general structure. And we also wanted to make it very easy to target a new machine. We're also interested in architectural studies. So what it takes to describe a machine so that you could do that allocation on the machine should be very simple. And in fact, in our approach, you just need to give us the register classes up here and the alias sets, and then the allocator does all the rest of the work for you. You don't have to write any machine-specific code. That's the wrong direction, sorry. So at a very high level, what did we do to solve this problem? Well, we kept the interference graph, which is the heart of a graph coloring register allocator, exactly the same as it was in Chaitin's world, which is different than almost all of the other approaches that have tried to solve this problem. Nodes are simply representing register candidates. Edges are representing the interferences between candidates. If two candidates are live at the same time, you obviously can't use a single register to hold both of their values. And we're simply, in our world, trying to find register assignments that allow us to stay out of problems with aliasing. So this little graph down here is supposed to represent an interference graph with a couple of different register candidates. And Chaitin solved the graph coloring problem by using a very simple little criterion that said, I want to know if a node in this graph is trivially colorable, where the colors correspond to the number of registers that I have in the machine. So if I have k registers in my machine, I know if a particular node has a degree less than k, it's trivially colorable. No matter what my neighbors do, I can always find a color for it. And we'll be able to remove that node from the graph, and through simplification process and so forth, you can end up coloring the graph or do some spilling. So what we did in our work was start with this colorability criterion and try to adapt it for the violations and the assumptions that we saw on the previous slide. And let me just give you a quick view of what's going on there. On the right-hand side, K was simply representing the number of registers available to a particular candidate. And this is really easy. If I'm thinking about candidates coming from particular register classes, I just need to know the number of names in that class, and that's my bound K. The interesting side of the world is over here with degree. Degree is no longer going to work for us. But what degree was representing was the maximum number of available registers that could be consumed by some coloring, a worst-case coloring of my neighbors. And what we need to do is come up with a way of calculating a value on this side, which we're going to call squeeze, which is exactly this constraints applied by the neighbors. This is where all the interesting stuff comes in. Unfortunately, in 12 minutes, I'm not going to be able to tell you about all the good stuff. So I'll just flash some math and say, this is what we do. There's machine-specific stuff in here. There's program-specific stuff in here. And in particular, this is a recursive calculation based on a class tree. And the interesting thing with the class tree is, again, it's machine-specific information. This class tree directs our computation so that we end up with an approximation that actually, for most modern architectures that we know of, gives you an exact approximation to what you did if you went through and tried to say, what is the worst case in an exhaustive way coloring of my neighbors? So What I want you to do is come away from this part of the talk saying, wow, he's doing a whole bunch of different things. He has to understand liveness information. He has to understand some stuff about the program. He has to understand some stuff about the particular machine. These are all aspects that we want to see how well we can support within Pheonix. So what I'm going to do now for the next couple of minutes is go through our experience with Pheonix, starting with Pheonix in general, how it was to move from our current compiler infrastructure to working within Pheonix, diving down into the fact that we're trying to do machine-specific kinds of optimizations here and looking at what it takes to encapsulate some of the target specifics, and then continuing down into the deeper bowels of Pheonix and looking at what kinds of support we had in different areas. So, as I mentioned, we did our original work in machine sweep, and one of the really nice things that we found with Pheonix was that not only were there common goals, both infrastructures were trying to do precise manipulation of machine instructions. We're trying to make it very easy for you to retarget the compiler to a new machine out there. But we found that with these common goals, we ended up with intermediate representation, which was very similar, which made us very happy because it made it easy for us to port our code over. It made it easy for our students to get up and working on the infrastructure. So there's abstraction of machine instructions over this. You don't have to always know specifically what's happening in your target architecture. You can manipulate them in machine-independent ways and then just ask for particular properties that are of interest in your particular optimization you're trying to do. All of the operands are explicitly named so that you can see data dependencies directly. There's an integrated CFG so that you understand what's happening with the control flow. And a lot of extra information is carried around in annotations, which helps you in extending the compiler system. So looking at the target specifics in a little bit more detail, there is, in both systems, an API that gives you access to the target characteristics that you liked. And for our work, we found that most of the kinds of questions that we wanted to ask about a target machine, there was already pieces of the API to answer those things like register file characteristics, instruction properties, and so forth. It's not to say that they were all in there. Hoi and his group were very responsive when we came across ones that were missing. But for the most part, you can get started right away doing machine-specific optimization with the system. Implementations are derived from machine descriptions, which fits very nicely in what we were trying to do with our register allocation framework. Didn't want to have to write code just to get the system up and running on a new machine. And then finally, one of the really nice things is there's a general purpose lowering API, and what we mean here is I don't really care what the target machine is. For example, with register allocation, I know I need to do a spill into memory or a restore out of memory, and I don't want to know exactly what instruction in the target machine does that. I can say it in a machine-independent way, and the system will generate for me the correct instructions. So that was quite nice, too. So, as I mentioned earlier, what we did was we actually replaced a phase here. And this is probably where we ran into the most trouble. This replacing of a phase is a little bit harder than you might think. First of all, for doing things in a target-independent way, getting access to the right set of APIs for that. But more importantly, it's understanding the contract. Here we are sitting in a register allocation phase. I'm not really sure what happened before me, and I don't really understand what the passes that occur after me want to have be true. And so that's one of the things that we've been working with Hoi and his group on is better understanding and better documentation for the contracts that exist before and after particular phases so that it is really easy to come along and insert a new phase. Pheonix does a very good job of providing all the plumbing so I don't really have to understand how to get a phase hooked in. It's a very simple set of methods to get your phase hooked in. Again, it's the contract that's the really hard part here. We benefited a lot from an early sample that showed us how to do that, in particular the linear scan sample, but again, a wider variety of samples that could show you a couple different things would certainly be beneficial here. So the Pheonix API itself, so we didn't do any extending of the intermediate representation. We're not adding any new instructions to the world, but we did define a lot of new data structures. We talked about interference graphs. There was no interference graphs in the system before we came along. Talked about this class tree. Talked about sets of registers that we needed to handle and so forth. So we extended and built off of the Pheonix infrastructure in a bunch of interesting ways and found it quite good. There wasn't really any problems doing that there either. And we did use some of their existing analyses. For example, liveness information was important to us. So the other big thing for me personally, I had never written any managed code before I did this little project. And as you heard in John's talk a little bit earlier, if you were there, the plug-in model requires a managed phase. So I had to learn how to do that. And probably this was a little bit more surprising to me to go from C++, which is what our original code was, to manage C++. Sounds like it's the same thing. How much is this little managed word going to really affect us? It actually affects you a lot more than you would expect. And I understand from the new versions of managed C++, this will be a little bit easier. But that is something, if you're going to go from a C++ to a managed C++ world, that you should be aware of. I do believe this is the right thing to do, though. And we're excited about writing our compiler passes, phases in the Pheonix terminology, in managed C++ in the future. We absolutely think it's the right thing to do. Ben?
When you consider using C# instead of managed C++, what was the...
Yeah, now I'm an old guy, making me really pushing me here. So the question was, would I consider using C#? So the little bit I have been reading about managed C++, they keep bringing in C# every time. So yes, I definitely would. I think the managed C++ in the long term is going to be best for the kind of research I'm interested in, because every once in a while I do want to get down really grody, do some bit manipulations, and I need to be down at the machine level.
Mike, can you elaborate a little bit about the managed C++? What makes it hard?
Can we hold a question to the end, because we have one
more
to go.
Yeah, I'm almost done. This is my last slide. So we were trying to do some performance things. This is basically where we are today, understanding better what kinds of hooks and support we have to measure the time that we spend at compile time and the time that we spend at runtime. So that's all I have to say.
Thank you. We have one more to go. And this will be Brad Palmer from UCSD.
Okay. At UCSD, we've been using Pheonix to basically do basic block profiling. And we've been using this to guide our phase-based research for x86 Windows applications. And so what I want to do in this short 10 minutes is first summarize what we do for phase-based analysis, and then show you a few example slides on some example code from using the Pheonix API to do the basic block profiling. Okay, so first off, to spend a few slides on what we mean by phase-based analysis. I think it's generally known that programs have repeatable behavior, and this repeatable behavior is time varying. It changes over time. Okay, and so we want to have an automatic technique just by looking at how the code is executed to identify this phase behavior, to potentially guide simulation, adaptive hardware, software optimizations, and OS scheduling. Okay, and we want to do this very quickly using a sort of a code profiler, like basic block profiler. Okay. So what do I mean by phase-based analysis? So here we have a program gzip, and what's shown here is the time-varying behavior for different hardware metrics. So on the x-axis, what we have here is we've taken the program's execution and we have broken it up into intervals of 10 million instructions. Then for each interval of execution, for 10 million instructions, we plot what's the average IPC, branch, etc. miss rate. And as you can see, as you execute gzip over time, the behavior varies from an IPC of 1.3 to 2.0. And what we'd like to do is be able to exploit this behavior. Most compiler optimizations, hardware optimizations are targeted at aggregate average behavior. But we'd like to be able to target these two different behaviors. And we want to do this analysis very quickly offline, and we do this with a code profiler. And our interest in using Pheonix is that we want to have access to Microsoft applications and be able to do this analysis on Microsoft applications. Okay. So two definitions before I dive into exactly what we do for phase analysis. First is an interval. So we break the program's execution up into these intervals, which is just a contiguous stream of instructions. So each interval might be, let's say, 10 million instructions. Okay? And the focus of the phase analysis is how do we take these intervals and then group them together so that intervals that have similar behavior will be put into the same phase. And you can define similar however you want to. Okay? So we want to take all these intervals through a program's execution, group them so that all the intervals that are put into the same phase have similar behavior. So going back to our example for gzip, if we actually did phase analysis, you might group it into these three phases, where we have a red, a yellow, and a blue. okay, where all of the 10 million intervals of execution, I think I forgot to say that, on the x-axis here, this is in billions of instructions. Each 10 million instructions, each 10 million interval, for example, in the red, has the same behavior, the same for the yellow and the same for the blue. And we would like to do this analysis without having to look at any hardware metrics, just in terms of how the code's executed, using basic block profiling. Okay? And one way we actually use this technology right now is to use a tool called SimPoint to guide where to actually do your sampling for simulation. Now, this also could be used to do sampling for getting code profiles or other profiles for compiler optimizations. So if we have this phase analysis for gzip, well, then we only really need to take one sample from each phase, one from the red, one from the yellow, and one from the blue, and then we do detailed analysis on that 10 million instructions, and then we can get a complete representation of the whole program's execution in a significant reduction in amount of time. Okay, and we've shown that we do this for the whole benchmark suite, and we can get within a 5% accuracy error of the overall execution of the program. Okay, so to do this, we do this by using basic block profiles, and then I'll show after this some slides of using Pheonix to do that. The goal is to track the behavior of the program, because the behavior of the program and what procedures you execute and how you execute directly correspond to the underlying hardware metrics. Okay? And we do this by creating code signatures. So for every 10 million instructions executed, we create a code signature, which is just a vector of basic blocks. Okay? So that vector of basic blocks, so where each dimension in that vector is each static basic block, we can actually then take two different intervals and compare the vectors just by doing a Manhattan or a Euclidean distance. So if you use Manhattan distance, if the two vectors have a difference of 0, that means they're identical. If they have a difference of 2, that means there's no overlapping execution in their code. Now, if two intervals of execution have a difference of 0, then they will have, we've found, have the same underlying hardware behavior. Okay? And we can do all this analysis by only looking at code profiles. Okay. So using Pheonix, one of the goals for this was we want to actually do this profiling behavior and create these phase analysis points and map them back to the source code. So one of the things we want to examine is the same phase behavior seen across different compilers, different operating systems, and different ISAs. And we found that to be so when looking at the alpha ISA versus x86 and the alpha compiler versus the Pheonix compiler, which I'll show a few slides on. Okay. Now, the next two slides I'll show the API code that we use to actually build the basic block profile. And when building a basic block profile, there's actually two parts. There's the instrumentation tool, then there's analysis code. So if you want to build a basic block profiler using Pheonix or other binary instrumentation tools, you first build an instrumentation tool using the Pheonix API to actually traverse over the control flow and to actually insert your hooks. Then you also create an analysis piece of code. And in the analysis code, that's where you collect the profile information, then write it out potentially to a file. Okay. So in our example here, sorry about showing source code, but figured it'd be useful in the demonstration here. So the first thing we do is we have created a library, a dynamic library that has the analysis code, and there's a routine there called track basic block that we want to actually call to do the profiling of the basic blocks. Okay, so the first thing using the Anvil API here is we get a pointer to that routine in the analysis library. Okay, then once we have a pointer to that routine, we can then insert calls anywhere in the binary to that routine. So when we use Pheonix, we're going to take an original binary, we're going to read it into the Pheonix IR. We're going to insert calls in there to our analysis code. In this DLL, we're then going to write out the new binary. When we run that new binary, we're going to get the profile generated. Okay? The next step is to traverse over all the structures in the Pheonix IR so that we can actually add our instrumentation calls. So Pheonix allows us to basically traverse over all the functions in the binary. We can then raise the function to the Pheonix IR, and then we can traverse over all the instructions in that function. Okay? Then for each basic block in that function, we actually add a call, passing in a unique basic block ID and the number of static instructions in that basic block. Okay? And Pheonix is actually has a lot of features in terms of actually doing binary instrumentation and binary modification. So to actually create this call, it gives you the ability to create your own instructions. So the first 2 lines here, what we do is we actually create a procedure call x86 instruction using the Pheonix IR. Okay? And then we add to that procedure call the 2 arguments we want to pass into our profiling routine. So the first argument here we add in is going to be the basic block ID, and the second argument we add in here is going to be the instruction count. Once we have created this instruction call, we can then insert at the start of the basic block this instruction into the new binary, and then when you write out the new binary, we have the ability to generate our basic block profiles. Okay, so that's all the source code I'll show. So how does this work for finding phase-based behavior? So what's shown here is what we call a basic block similarity graph. We took the basic block vectors that were generated from Pheonix. So every 10 million instructions, we outputted a new vector which represented how many times each basic block was executed in that 10 million instructions. And the diagonal here represents each 10 million instructions. And what's shown here on going right and up is the similarity of each 10 million interval with other 10 million intervals. So for example, if you take this 10 million interval and compare it to this 10 million interval, and you do a Manhattan distance, if you get a distance close to 0, meaning they're identical, we actually print here a dark color. If there's no similarity, we print a light color. So for example, if you take 2 intervals from the blue phase, we find identical behavior. Then if you take an interval from the blue and the yellow phase, we get a difference of 2, meaning that they're very different. And this was all done for gzip using the Pheonix API. Now, one thing I was just going to show you here is that we did this analysis using the Pheonix API, and this is the similarity graph. And then we did the same analysis using the alpha ISA with Atom, and we get very similar, almost identical phase behaviors that we can see. And even looking at more complex programs like bzip here, where for bzip, this shows that this part of execution is very similar to this part by this dark square here, and these parts of execution have similarity by this dark gray, and this phase and this phase are somewhat similar, but much more different than the other ones. But the point here is that we're able to find this phase-based behavior using the code, and actually the phase behavior is extremely identical between the different ISAs, the alpha ISA being RISC and the x86 being CISC, and also very different compilers. Okay, so the goal, since we're able to find these similar behaviors between ISAs, what we're trying to do, for example, for the spec programs, is to provide spec level, source level simulation points. So if you're running a given input for a spec program, if this loop executes n times, then start your phase analysis at that count of that loop iteration, and have that work across all different compilations and ISAs. And that's what I have. Ben?
Can you insert code markers into the source that actually say start the...
That's what we're looking at doing, is inserting the code markers into the source, so that, and providing these so that, for example, you can use them for the whole spec suite, no matter what ISA or compiler you're using.
Any other questions for the early adopters, or for me?
Back to Mike's question about management.
Okay. Sorry, those were Wenmei's questions about...
Yeah. It's just, I was just wondering about the managed versus unmanaged C++.
Okay, so the question is about unmanaged versus managed experience. So, Mike.
So if we skip right by the part that says, oh, I know C++, therefore I don't have to read anything about managed C++, can we just skip by that part? So some of the things that we came across, and Glenn Holloway, who's also in the audience here, who did a lot of the coding too, can chime in whenever he would like. We used a lot of templates in the original implementation, and generics are coming in the next version and things like that. And I believe John mentioned it in his talk too. The code sample that we had was set up to compile both for managed and unmanaged, or I should say, I was told to say native world, which is confusing, right, to follow along with both styles and trying to understand as opposed to following one style. So some of it I think will go away, both as time moves forward and people become more comfortable with one versus the other, and as a lot of the uglinesses, I think, and Hoi can correct me if I'm wrong, that were in the original managed C++ were hidden behind macro definitions inside of Pheonix, and then when you pull them apart, it just gets a little confusing. So those were the kind of very nitpicky little things that gave us stumbling blocks to getting us to move forward quickly. But I think they're all solvable. I don't think there's anything definite here. Yes?
Just to be clear, one that probably you mentioned for the language had a lot of issues with release, which you guys are building on top of, about ready to product. And there the language is pretty much seamless between native and managed. You can use templates or generics on managed type. So in your implementation of whatever you're building, while Pheonix probably will not leverage templates, in its programming API, you can definitely use template framework. The new language is all spec. It's also being standardized. It's going through a standard process. In fact, the groups here. We do feel like most of the compelling features from C# are in the new. That should get a lot better going forward. And you can just leverage all your existing C++ code in conjunction with
Definitely looking forward to that.
Any other questions? So with that, I would like to thank our 3 early adopters and the Pheonix development team, without whom all I can just say that how interesting it is, but none of the action will be happening. So thank you, everybody. So.